What would happen if the sun suddenly turned into a black hole? Most people picture Earth getting pulled straight toward the darkness, but it wouldn't. Give that black hole exactly the same mass as the sun, Earth would keep orbiting almost exactly as it does now. The sky would go dark, the planet would become extremely cold, yet Earth would not suddenly fall into the center. That result sounds wrong if you imagine a giant cosmic vacuum cleaner, and that familiar picture hides what makes black holes genuinely dangerous. A vacuum cleaner creates moving air that carries nearby dust inward. Space has no stream of air rushing into a black hole. A black hole pulls through gravity. Gravity already controls planets, moons, stars, and entire solar systems. From far away, mass and distance determine the gravitational pull. Replace an object with something equally massive, and distant gravity stays equivalent. The name black hole makes the pull sound like a new force. Gravity remains gravity. That is why stars can orbit black holes for long periods. Orbiting objects provide some of the evidence that black holes exist. Instant suction would leave nothing circling them. So, what changes when a star becomes a black hole? The mass can stay the same while its size collapses. The sun's radius is nearly 700,000 kilometers. A sun-mass black hole would have a horizon radius of about 3 kilometers. The same mass would fit behind a boundary smaller than many cities. Earth would still sit about as far from that mass as before. At that distance, its orbit would have no reason to collapse. Reaching the dangerous region would require getting vastly closer. Compactness is the crucial difference. This remains a thought experiment. Our real sun lacks enough mass to end its life this way. Still, the imaginary replacement exposes the misconception perfectly. A black hole gains no magical reach across the solar system. Its defining feature appears close to the compressed mass. That feature is the event horizon. The horizon marks a boundary in space. It has no solid floor, shell, or wall. A spacecraft would feel no impact from touching its edge. Crossing it changes whether any signal can return outside. Outside the horizon, escape can remain possible. Inside, light can no longer carry a message back out. The horizon is the line where leaving stops being an available path that gives us a better picture than a hungry mouth. Think in terms of routes, speed, distance, and boundaries. Imagine sending two cameras toward the same supermassive black hole. Their starting paths differ by a small amount. The first camera approaches the horizon and swings around it. Gravity bends its path sharply. It completes part of an orbit and heads back outward. The camera survives because its route stays outside the boundary. The second camera arrives along a slightly different path. It crosses the orange ring. No wall appears. No explosion announces the crossing. The camera has passed the last route back to the outside universe. From there, its signals cannot reach the observer. NASA has visualized both versions of this journey. One trajectory loops out, the other passes the point of no return. Being nearby does not guarantee capture. Your trajectory and energy determine whether you pass, orbit, or cross. Surviving the horizon still leaves another problem nearby. Gravity grows stronger as you approach the black hole. More importantly, its strength can change sharply across a single object. The front of your spacecraft sits closer than the back. The front feels a stronger pull, the back feels a weaker pull. That difference stretches the spacecraft lengthwise. It also squeezes material from the sides. Astrophysicists call this process spaghettification. The name sounds playful. The mechanism is a tidal force. The critical factor is the difference in gravity across you. Black hole size creates a strange twist here. A stellar mass black hole has a much smaller event horizon. Near that horizon, tidal forces can become brutally uneven. A supermassive black hole has a vastly larger horizon. The force difference at its edge can be less extreme. You might cross the giant horizon before tidal forces tear you apart. The smaller black hole can damage you earlier. Now look at the famous orange image of a black hole. The glowing ring is material outside the horizon. Gas orbiting nearby can become extremely hot and emit light. That surrounding structure is called an accretion disk. Some black holes have bright disks. Isolated ones may have none. The black hole itself remains dark. Light from within the event horizon cannot reach our telescopes. What we see is glowing matter and a dark shadow. That shadow is larger than the event horizon. Warped spacetime redirects light around the black hole. Far away, light appears to travel along familiar straight paths. Near the black hole, those paths bend. This bending distorts the disk and anything behind it. Some light can loop around the black hole before escaping. Those winding routes help create thin photon rings near the shadow. The disk can also look brighter on one side. Gas on that side is moving rapidly toward the observer. The opposite side moves away and can look dimmer. The famous ring is a map of moving matter and bent light. It is not a photograph of a solid black surface. In 2019, the Event Horizon Telescope revealed the image of M87 star. M87 star lies about 55 million light years away. Its mass is about 6.5 billion suns. Capturing it required a planet-sized network of radio telescopes. Their combined observations reconstructed the dark shadow and glowing surroundings. Our own galaxy contains a central black hole called Sagittarius A star. It has roughly 4 million times the sun's mass. It sits about 27,000 light years from Earth. Its image was released in 2022. The gas changed within minutes. While the telescopes gathered data, scientists were reconstructing a subject that kept changing during the observation. Both images reveal black holes through their effects on surrounding light and matter. Return to our imaginary solar system. Earth keeps circling because the central mass has stayed the same. Move Earth dramatically closer, and the available paths begin to change. Some paths pass around the black hole and escape. Some remain in orbit. Some cross the event horizon. Outside that boundary, the map still contains routes back out. Inside it, every available future path leads deeper. That is the mechanism the vacuum cleaner picture completely misses. At a distance, an equal mass produces the familiar gravitational pull. Up close, compactness creates extreme tidal forces and severely curved paths. The event horizon marks where escape disappears from the map. And now you know. The frightening part was never cosmic suction. It was crossing the boundary.